and gentlemen, welcome to another computer science Colloquium. Next week, we have no Colloquium because it's spring break. The following week after spring break, we'll hear Jason Shankle from the, well, he's been here so many times, I don't know exactly what he's talking about. I think the same stuff. Today I have the special pleasure of introducing you to Scott Gordon, Professor of Computer Science at California State University in Sacramento. He used to be one of our faculty here, and then he escaped. He's going to talk about how Norwegian fishing boats pack their sardines, but most importantly I want to tell you a secret. He is world famous for his asphalt museum. Let's welcome him.
All right. Well, thanks, George. Happy to have a few familiar faces in the crowd. So this talk is about some research that I've been doing for the past year or so, off and on, and mostly the last couple of months since I've been on sabbatical. But the thing that you might find the most interesting about it is this kind of new technology that is right here in your backyard in Pembroke that you may not be aware of. So this company in Pembroke is called General Vision, and they make neural network hardware, and it's being used for a variety of things. And so I'm going to talk about an idea that they had and that I and a couple of students are trying to get working. I don't know what this is about. I like growing tomatoes and I like playing ping pong. So, and when I found out there was a variety of tomato called a ping pong tomato, then of course I had to grow it. It makes tomatoes the exact same size as ping pong balls. It's nothing to do with the talk. It does look like a couple of eyes, though, I realize. So, first of all, let's talk about video tracking, or tracking using a computer. A lot of times when I mention this research to somebody and I describe what I'm doing, they say, well, what would you use that for? What would be the application? What's the practical application? And I'm just amazed that somebody would ask that question, because of all the things you could do with a computer, this seems like one of the most obvious things that could have universal application, to basically replicate what our eyes can do, to follow and watch things. So here's just a very small number of ones that I think would be kind of obvious. If you can look at the computer, if your computer could look at you, then that would, of course, mean a lot for computer-human interaction. Obviously, it can be used and is being used for surveillance. The military applications are obvious because you might want to track an enemy plane or aim something at it while it's moving. Medical imaging, of course, it's being used there. Video games, it's being used there. And robotics, too. So I'm sure that you could sit down and in about 30 seconds come up with 10 or 15 more applications for video tracking. So needless to say, there are thousands of people around the world working on automating tracking. It's not typically been my area of research, but it's what I've been working on lately. An example that some of you may be familiar with that does tracking is the Xbox Kinect. Probably some of you have one of those. Does any of you have an Xbox Kinect? I'm surprised, actually. It's capable of allowing you to play games in which you yourself, your own movements are tracked and then become part of the game. And the way it turns out, this is the fastest selling electronic device ever. It's in the Guinness Book of World Records for And the way that it does it, as we're going to see, tracking in real time in 3D is a hard problem. And the way that the Kinect does it is not the same way as we do it. It doesn't actually look at something, figure out that's what I'm tracking, and then go straight off the image. What it does instead is it projects its own light, and it projects a light that's outside of the visible spectrum, a pattern of bars or a grid. It's called structured light technology. And so what it does is it has a sensor that looks just at that light. And so it's expecting to see a uniform grid. But wherever that grid is bent, it knows there's something there. And so that's how it tracks it, is by looking at perturbations of its own light that it emanates. And it turns out to be a pretty successful technology for doing that. Of course, that also limits what it could track. You know, it couldn't track something like a cloud, or it couldn't track something quite a distance away, or it couldn't track something on a video screen. But it could track something around the room as long as it doesn't absorb the light that it's emitting. It's a pretty clever idea. There's other devices out there that employ different types of technology. For instance, the PlayStation Move, that's a wand controller. That's this one over here. It tracks your movement by just watching the little light. And that's pretty simplistic, but it does one really clever thing. And that is, this light is capable of emitting a lot of different colors. And so what the system does is it looks around the room and sees what colors are out there already. And then it picks a color that's not out there, and it tells the wand to use that color, and that's how it tracks it. There's a whole bunch of devices that fall into this area called gesture recognition that are all about watching for particular kinds of human movement, hand gestures, nods, and things like that are purely focused on certain types of gestures, and that's how you interact with it. So here's a couple of technologies based on gesture recognition. So let's see, there are some specialized systems for faces and eyes. People have discovered things about our faces, like our faces have a sort of fingerprint, which is the ratios of distances between different parts of our faces, like the distance between our eyes and the distance between our nose and our mouth, and the width of, I don't know all the things, but if you measure a bunch of things, it turns out that yours is pretty unique, if certain of the set of the ratios. And so you can recognize a face that way. You know, that's not how we do it, at least we don't think. But, and similarly for eyes, obviously there's systems for doing that. One of the most exciting pieces of research out there now is, what you might want to do is, before sometime this week or whatever, Google the predator tracking system by Zdenek Kalal at the University of Surrey. And he's doing some pretty amazing stuff, probably the state of the art right now for tracking kind of arbitrary objects. And he's using a continuous learning model that's pretty exciting. So that's something to watch for right there. It's getting a lot of press. Okay, so that's tracking, but what about the title of the talk was stereoscopy. So let's talk a little bit about binocular vision. So what is meant by binocular vision? So you take the word binocular, you're looking through a pair of binoculars. Let's look at it in a different way. We have two eyes, and because we have two eyes, we have something called depth perception. It enables us to tell how deep something is, how far away something is, not just see, you know, sort of in a flat way where it is, but we can sense how deep it is. And that's really easy to mimic on a computer. Say a dog is running by. Your brain, or your eyes rather, both will point because your eyes move around. Both your eyes will point towards the dog. Your brain knows how far apart your eyes are. And your brain knows how far each of your eyes have turned. And believe me, if you sat down for about 20 minutes, you could do the trigonometry and figure out what D is. So that's really pretty simple, actually. I mean, it's high school trigonometry to do that. You have to get organized a little bit and draw some pictures and remember, is this a tangent or a sine and stuff like that. But that's about all there is to it, to gain depth perception. So we have the problem of we got to get these guys tracking. And once they're tracking and once they're actually moving, so that we get those angles, then we can do the binocular vision and detect the depth, or the distance rather. There are some challenges for the tracking part of this, however. It's really computationally intensive to track something using traditional computer vision techniques. Because as soon as you're talking about computer vision, you're talking about an image that has lots of pixels that have to be analyzed. Usually you have to do some sort of compression to make it tractable. And then when something moves, you have to do it all over again. So there's a lot of math that has to be done pretty fast in order to get any sort of speed out of the tracking at all. Also, it's complicated by the fact that things in the background may look a little bit like the thing you're tracking in some way. So you have to have a good model that can separate what you're tracking from what's in the background. Unless you're lucky enough to have a situation where the background is steady, then that's a big deal. Another big deal is lighting variations. Cameras are not as good as our eyes are at dealing with dynamic range. Our eyes and ears are pretty amazing, actually, in their ability to work with wide dynamic ranges. So things like if you just try to take a picture with a camera in this room, you wonder why does it look so dark, when to us our eyes have just adjusted and it's totally wrong. But also, when you model something and you're going to track it, as that thing moves around the room and just moving from being right under a light to being between the lights to being under a light to being on this side of a light, you've got the same image that maybe is bright, dark, light on this side, but dark on this side, light on this side, but dark on this side, with shadows going down. I mean, you have to model it in a lot of different ways in order for you to be able to track it as it's moving through a non-uniform type of environment. So the actual appearance of the target can change as it's moving. Another big one is actually doing the learning to do that modeling can be slow. If you want to track somebody's face, then what you have to go through to have your system model that face may be slow depending on the method that you're using. The stereoscopy is the easy part. It's the tracking that's the hard part. So let's change gears entirely now. We're talking here about tracking, which is, I don't claim to be an expert in tracking, and I don't claim to be an expert in image processing. My area of interest is artificial intelligence and neural networks and evolutionary computation and stuff like that. And so if we try to tackle this problem using a neural network, let's just take a look and see what's a neural network. There's a lot of different kinds of neural networks. I'll briefly show you two of them. There's the most common one is called a multi-layer perceptron, at least it's sometimes called that, or a feed-forward perceptron type of a neural network, where you have these artificial neurons that are connected, and we call them artificial neurons. Of course, our own neurons are a lot more complex, but in an artificial neuron, the idea is to sort of model it or inspire it from our own neurons. Remember, let's see, what do we know about our neurons? We don't know a whole lot, but we know some things about them. They fire or they don't fire. If they fire, then they exert pressure on their neighboring neurons. The more pressure that a neuron gets from neighbors, the more likely it is to fire. And so they're kind of a binary behavior. So we can model that, and so the pressure exerted from neighboring neurons in a multi-layer perceptron is in one direction, from the inputs to the outputs. If we're going to use this for image tracking, we'd have to actually put an image into here. that means a lot of neurons just to capture the image. So we're going to have to do a lot of image compression, some clever image compression to do this, and then we're going to have a lot more than is shown here. And if this is a JPEG image or something like that, you can imagine how many nodes and how many connections there are going to be. And we'd have to train that thing. And training means that setting all these weights to appropriate values so that it can correctly classify different images that it sees. So it turns out that is a powerful model because, like our brains, the knowledge when it learns things seems to get distributed around the neurons rather than just localized into individual neurons. You don't have a little set of neurons that remembers what a cat is, or a puppy dog walking by. And if you remove those few neurons, then you don't know what a cat is anymore. The notion of a cat is distributed amongst probably millions or billions of neurons. And those neurons are sharing, learning multiple things. So that turns out that's got a lot of advantages because it means that your system can actually generalize. Maybe you train it on 3 or 4 cats. Turns out it's learned how to recognize other cats. That's handy. That's called generalization. The big problem with these is they're so slow to train and learn. It might, for something as complicated as how to recognize a cat from a dog, you might have to train this thing for a week. That rules it out of a lot of applications right there. There's another type of a neural network. Actually, like I said, there's many types. One other type is called a radial basis neural network. And this has a similar architecture, multiple layers in which we would feed the input image on one end and the output classification would come out. The output's at the other end. However, the role of the neurons inside is a little bit different. And instead of each neuron functioning essentially the same way as our neuron does, or it seems to, is instead of having a sort of a threshold, these ones in the middle here use radial basis or kernel type functions to model some feature. And so we call these middle nodes radial basis nodes, or because inside of them they implement usually some sort of a Gaussian function that either loosely or tightly responds to some particular feature. And then the output may be either a winner-take-all or some threshold type combination like the other neural networks. But what this means is that if you do and I won't go through all the math of how that's modeled, but the end result is that instead of the knowledge being distributed, you may really have 1 or 2 neurons that's job is to know what a cat is, and another one to know what a dog is. So it's more localized. That means they usually don't generalize as well. If you learn a couple of cats, you know those cats, not cats in general. But they're usually faster to train, sometimes a lot faster, depending on the method that you're using. So the technology that we're going to describe uses this approach because of the speed of learning, primarily. All right, so the particular neural network hardware that I'm going to show you is called CogniMem. It's made by a local company here called General Vision. It's a very small company, but it's been around here for something like 15 years. It uses that kind of localized approach, but it's highly parallelized. And so, for instance, if this is slightly oversimplified, but if we had, say, a certain number of neurons trained, such as each of them was trained on to recognize a particular fruit or a particular vegetable, and then we show it some other picture, if it's not too perturbed from the one that it learned, then each of the neurons would respond to some sort of an output that was a distance metric, how far away it is from what it knows. So each neuron has a memory of what it is that it knows and a category. And so in this case, the one that would output the smallest distance metric would be the best match, and hopefully it would be the carrot neuron instead of the banana neuron. And what makes the chip rather special is the degree to which they've parallelized everything. So whereas in a regular neural network, when I said as you've got an image with hundreds or thousands of neurons in it, it would take forever to do all that processing on a computer. In this case, it doesn't matter how many neurons you have, it takes the same number of cycles. In fact, you could have 1,000 neurons and it still takes 17 clock cycles to get your result, which is pretty blazingly fast. So it's highly parallelized. It uses radial basis function type nodes. The chip out of the box comes with 1,024 neurons on it, and you can daisy chain them side by side, and I think if you daisy chain them, you can daisy chain up to like 1,000,000 neurons, and they still all work in the same time in 17 clock cycles, I think it is. So the speed is independent of the number of patterns that you want to learn. The nice thing about that is, remember, this thing generalized very poorly. So if we just learn 1 or 2 cats, it's going to know those cats and not any other cats. Well, since it doesn't matter how many neurons we use, it runs just as fast, we could just learn a whole bunch of different cats. So we can mitigate that generalization problem by just using more of the neurons and learning as many examples as we can. Here's what the chip looks like. It's a square, and it's got pins all the way around it, and it's about this big. And it says Cognimem. It's called a CM1K, Cognimem 1000, because it's got 1,024 neurons on it. If you look real close, it kind of looks pretty boring, kind of like this. Just a giant bus with 1,024 neurons on it. They also, if you just have that chip, it's not like you can plug it into your computer and start using it. I mean, you have to be able to communicate with it. And so they also produce a bunch of little boards that have different functionality that use it. Their most popular board right now is called the V1KU. And this is the size of the entire board compared to a dollar bill. That's why the dollar bill is there, not because it costs $1. It costs a little bit more than $1. But it's there to give you an idea of the size of the board. And it's got on it a camera. On this one board, it's got a camera, it's got a little processor, it's got an FPGA with some control software so that you can use the neurons, and it's got a CM1K on it, and it's got a USB port. It's got a couple of other things on it too. These are what interest us. That V1KU is getting used for a lot of applications out there. Let's see, the top 2 are the ones that have been the most lucrative for the company. And the first one is, I believe, in Japan. There's some rather large glass manufacturers that save a lot of money by automatically detecting. They make large sheets of glass. If there's a little imperfection on it, then the glass sheet gets returned and they have to make a new one that's expensive. So detecting little imperfections, it turns out they were able to simply set up the V1KU on it and say, this is what glass is supposed to look like. And then they just run it down a track. And if it ever says, that's not glass, then they know there's a defect there. And it's been hugely successful for that and very fast. The fishing boat example, I don't know if you've ever seen any of those reality shows where you go and see the Nordic fishermen risking their lives to catch fish that only live up in the Arctic. And so it's pretty rough terrain up there. And they needed a device that could watch the fish that were caught coming in and see, is this a fish that we should pack or that we should throw back in the sea? And so that, and plus since it's just a little board, the cold or the dampness and the rough conditions there are going to be shaken up and stuff that wouldn't be so good on a laptop. This little board doesn't care. And so it's been good for that. They've got a little app you can buy that does kanji character recognition. So if you write it in Mandarin or Chinese, then this will scan it and read it for you. Then they've These are a little bit newer. These ones aren't actually in the production phase yet, but there are other third parties who've done research using face recognition, LiDAR imaging. I don't know if you know what LiDAR imaging is. If you don't, that's really, really cool. You should look it up. It's basically 3D immersive imaging where it's used a lot by geologists to look for changes in geology. People are just, for instance, earthquakes and other terrain that you can fly in and under and detecting cancer cells too. This is actually a picture of the V1KUs on a sheet of glass, and that's one of those Nordic fishing boats. It has some advantages over other methods. The CM1K, the actual neural net, it can take a whole bunch of inputs that doesn't have to be visual. It doesn't have to be faces or eyes. Like I said, it doesn't even have to be light waves. It could be sound waves, digitized, radio waves. The V1KU, it's attached to a camera, so you're presumably going to use that for light, but there's nothing limiting it to that. If there's a pattern it can look for and it's some sort of signal, then you could use it. It's off the shelf, it's not very expensive. If you get it on one of these boards with the FPGA, it's programmable. They have some software or firmware already available for it. You can, if there's not enough neurons there, you can, like I say, you can daisy chain them and make it as big and complex as you want. Okay, so what am I doing with it? Well, one of the things that they thought that it could be useful for would be to do stereoscopy. So, but they didn't have time to do it because they were doing some of those other things. And so I said, well, I and a couple of my students would like to try to do that. Gives me an excuse to learn C# and learn a little bit about some hardware that I wasn't familiar with. So they gave me a couple of V1KUs. And I went out and bought a couple of servo motors. And I couldn't figure out how to connect. A servo motor is a little motor, little electric motor with a thing that turns on it, and you can control the turning of the motor. Not being a mechanical engineer, I didn't know how to connect these two up because I wanted the servo motor to turn this like your eyes turn. So I used Velcro and rubber bands. Easiest way to talk to a servo motor is through a servo controller, so I bought a little servo controller from a robotics shop. And then took my laptop. Takes 3 USB cables to drive this thing, one for each V1KU and one for the servo controller. The servo controller that I bought, you can plug up to 8 servos. I ultimately am going to need 3. I've only got 2 right now. Because, let's see, your eyes, they kind of move independently, but they don't move up and down independently. Your eyes never do this. So I just need a servo motor that will move the whole thing up and down. I don't have that yet. I only have this business. And then I wrote a little C# application that moves the servos, tells us that based on what the V1KU sees, if it sees that the object is over there on the left, then I tell the servo motor to move to the left, try to keep that thing centered. If I keep each servo centered on the object, then it's like your eyes are pointing to it, and I can calculate that distance based on the angles that the servo motors are at any given time, using that formula that I showed you before. I didn't show you the formula. That's extra work, homework. Come up with a couple of simple learning algorithms for the V1KU. Let's say I wanted to track, I don't know, some object, maybe my fist or something. Then if I'm in learning mode, then I can put my fist in the field of view of the camera. I can specify a region of interest and say, I want you to learn what's in this portion of the image. Not because I don't want it to learn the whole thing. I want it to learn some part, something that it sees. That's RR, region of interest. So if I'm in learning mode, then I tell it, here's the region of interest I want you to learn. If it already recognizes it, then it doesn't add any neurons. But if it doesn't recognize it, then it's, oh, I guess I better learn that, and that's another neuron. There's also, you can also, in the application, tell it to unlearn something. And if you tell it to unlearn something, then that just sort of takes the Gaussian and squishes it so that it reduces the likelihood that that will be recognized by that neuron. So it will go through each of the neurons and say, if you thought this was something you should know, maybe you should squeeze a little bit so that you won't know it. So usually learning something is a combination of learning it at different angles and then unlearning some other things. Once you've decided, oh, I think it knows what it looks like, then I can ask it to track. And I've got a simple predictive tracking algorithm in there. There are, of course, better tracking algorithms. There are people who have studied tracking all their life, which I haven't done. And so mine is pretty simplistic. Here's what's in there now. I'm still working on improving it. The one I have now tries to look at where the object has been for the last couple of time steps, and then predicts, okay, for the next time step, if it's continuing moving in that direction, where should I expect to find it? And that's where it looks first. And so, and that's called the region of search. If I'm in tracking mode rather than in learning mode, then I don't have a region of interest, or something I'm supposed to learn. I have a slightly larger, what's called the region of search, where it's going to look to find it. And that region of search is moving with the object, hopefully, if it's tracking successfully. It looks where it's predicting it to be. If it is there, then it just moves the servo there. If it's not, then it says, all right, maybe it stopped moving. I'll look where it was and see if it's there. If it's found it, okay, well, actually, in that case, it wouldn't have to move the servo. Or actually, it might have to, it always has to move the servo a little bit because the region of search is slightly bigger, and if it's off-center, it'll try to zero in on it. If it doesn't find it there either, then it kind of goes into panic mode right now, and my mind could be a little bit smarter, but it grows the region of search, and uh-oh, where is it? And it starts looking for it and so it grows the box that it's looking in, and it keeps doing that until it sees it. And then when it finally sees it, then it moves the servo there. And once it has both servos locked on, then it can triangulate and tell you how far away it is and what its coordinates are. And then it can do its prediction of where it expects it to be the next time step, and you go back around again. So that's what it does, and this is what the prototype looks like. A little laptop, and my little piece of wood with the two servo motors, the servo controller, the servos held in place by the Velcro and the V1 KUs. And I have it with me right here on the table. And let's see, is that my last slide? Oh, well, before I actually show it to you, there's still things to work on. I really like Zdanek's continuous learning model, and I think it will work in this because of the fact that the reason I think the continuous learning will work on this is because when I tell it to learn something and it already thinks it knows it, it doesn't make any changes. So I could have it just continuously learn and or unlearn, and I think that would improve it a lot. My motion prediction is really, really simplistic, and there are better methods out there that I need to implement and test. The ultimate plan is, once this works pretty well, to move get rid of the laptop and move it all to hardware. Because right now, the bottleneck is .NET, and the whole thing is having to go through .NET. The image has to go through .NET, everything. It's amazing that it keeps up at all, actually. So if we can get rid of that, that would reduce the power consumption necessary, and I mean, you could actually stick it on a little toy. And I have to add the third vertical servo. If you're curious, the website for the company that makes all this stuff is generalvision.com. There's two generalvision.coms. One without the hyphen and one with the hyphen. The one here in Pengrove is the one with the hyphen. They got all kinds of cool stuff on their website. So I'm not here to plug them. I don't even work for them. They don't pay me or anything. I'm kind of, like I say, doing this as part of my research. But I think what they're doing is pretty exciting. They just opened an office in Folsom, hired 2 of my grad students. So I'm pretty happy about it. All right, so this system will work better if we have as much light in here as possible. Is it possible to increase the amount of light in here? Like, is it possible to raise it?
Yes.
That'll work.
Wow, it's really bright.
Because at least you can't see the light. That's right. I forgot, you guys are like creatures of the night. Now, you have to be very forgiving with this system because it's so very young. It's still learning how to track things. And sometimes it'll see something that it thinks is what it's supposed to track. Like the last time I demoed this, it was tracking something pretty good, but every time it saw a particular person in the class, I think I was having it track somebody had a little game controller with it, so I was tracking the game controller. But there was one guy sitting in the class. Every time that person was in the field, he would go, oh, that's it. That one person just kept zeroing in on that guy and saying, that's the game controller.
The crash algorithm.
What's that?
A crash algorithm.
That's right. So I had to tell him, just move to another seat so I can demo this thing. They also tell me that they just recently found a small bug in it, and in certain modes it adds some noise to the model. So once they debug that, it'll start working a little better too. All right, so let's see. I didn't come with anything for it to track. I haven't trained it on anything today, so let's see if I move this thing over here.
Uh-oh.
You know what happened is I think I got unplugged. You unplug this thing and it crashes.
So you hand-made this?
Isn't that obvious?
That's so sick.
We actually have a schematic for a machined version of this in all 3 dimensions that would be a big upgrade from this, but we just haven't actually done it yet. All right, so let's see if this thing's going to work now. Occasionally I find myself having to rebuild, which is a pain in the neck. Still got little bugs in it. Okay, and so the lighting in here is very good. I'm going to have to turn down the aperture a little bit.
Which way is it looking at?
Let's look in that direction. So there's Jordan back there. You can track it.
Looking at you.
We'll just see if he's the one that it doesn't.
Like in RoboCop.
All right, so that is a kind of a noisy background, so I'm not entirely sure it's going to do all that well on that. Maybe I'll turn it slightly to just in the interest of making it a little bit more likely to succeed. And so you can see there's 2. Sorry, it's so washed out. There's 2 images. This one is coming from this camera, and this one's coming from this camera. So no, I got that backwards. This is coming from this camera, and this one's coming from that camera. So I think I actually have them hooked up backwards. Let me see here. 2 should be. No, it's backwards. I got it backwards. It turns out they're numbered, and the order that they come in the USB makes a difference. So let's try it. If I have them backwards, they go like this. Signals. All right, so this is the one I'm doing, right? Okay, I got it right. Turn the aperture down. All right, so now I need something to track.
Ladine.
Go for it.
I don't know, something you know, like about this big or something that I can.
Like a
looks
pen
little
or something?
unique. What's it?
Pencil.
So maybe my keys. What's over here?
It's a cup of noodles.
Noodles? That looks cool. Let's go with that. Let's track a cup of noodles here. All right, so it's still a little bright. Let's turn it down a little bit more. Make sure we get a good contrast. That looks pretty good. You can see that's noodles, right?
Here it is.
Okay, so what I'm going to do now is I'm going to put the cup of noodles in the field of view of the left camera, and I'm going to tell it to learn the cup of noodles. And now it says it used 3 neurons to learn this. I'm going to learn it a couple of different ways. Actually, what I'm going to do is I'm going to check this box. It says enable recognition. And I don't know if you can see, but sometimes there's a little REC that appears there, and when it's not there, uh-oh. It still says right. That's not too good. Let's unlearn that. We seem to be in an odd mode here. It's supposed to not know that. Yeah, that happens sometimes. That's a bug that periodically pops up. Probably because I went through the porting, unporting thing. That's a bug we're still trying to track down. But let's just start all this up again here. Sometimes, for some reason, when it learns something, it learns it backwards. And then, of course, it does everything but track beyond that. Let's try it again. Let's learn the noodles. All right, it says it used 1 neuron. Let's go with that. Let's see here. Oh. Sorry. Which time? We're almost done. Let's try this one more time. Now it's sometimes the boards don't reset themselves, and failed that one time, it could be not completely clearing out from them. One more shot. Sorry. Let's see if this one's doing it. Yeah, unfortunately, it's not behaving. Yeah.
Oh, there it goes.
They got in a bad mode. The stereoscopy works, I mean, if I could get the thing reset, as you move the object around, they each point in and it does the triangulation and figures out the distance in inches, and the XY coordinates in this plane of about 2 feet by 2 feet, or 4 feet by 4 feet.
How far away are they from each other?
They're 1 foot apart. And this is the first time I've actually demoed it and had this happen. Basically, it's just backwards because of because it got me backwards. There's one more thing I can try, actually. Let me try one more thing. If I do this. And then try again. I've actually got it set to a larger size image. And it froze. Yeah, so we were in a bad mode. But maybe it may work the second time. Let me try to see. It's back to see if we get lucky this time. No. Fix everything else. Yeah, it's backwards. Yeah, I'm sorry about that. This is the first time when I've demoed this. So I can't show it to you actually tracking. Anyway, it means I have to reboot the machine and find out what we want to have.
That's okay.